When facing a situation involving pre-existing electrical work with potential code violations and altered permit circumstances, a strategic approach is essential. Firstly, clearly communicate with the homeowner about the identified violations within their electrical work. Explain that their work requires correction to meet current electrical code standards. Emphasize that the initial city permit no longer encompasses the additional electrical work they've undertaken without obtaining the necessary homeowner permit. Secondly, meticulously document all observed violations. Employ photographs and videos to capture visual evidence of the discrepancies. Supplement this with written notes detailing each specific violation. This documentation serves as a crucial safeguard in the event of future disputes or liabilities. Thirdly, define a limited scope of work that you are willing to undertake under the original permit, which includes the wiring for the furnace and air conditioning system. However, ensure that you only connect the home runs at the panel if the wiring was initially installed and inspected under the umbrella of the original permit. Advise the homeowner to proactively secure a homeowner permit to address the electrical work they've independently completed. Explain that obtaining this permit will mandate an inspection, guaranteeing that their work aligns with prevailing code requirements. Furthermore, clearly state the boundaries of your responsibility. Emphasize that you cannot assume liability for any electrical work that falls outside the purview of your permit or has been executed without proper permits. This explicitly includes the existing wiring that the homeowner has independently installed. Secure a written agreement with the homeowner that outlines the precise scope of work you are contracted to perform. This agreement should also clearly delineate the homeowner's responsibility for securing the required permits for their independent electrical work. Explicitly state your limited liability concerning the electrical work beyond the scope of your contracted services. Reach out to the city inspector to ascertain the current status of inspections for permits issued before the recent changes in ordinances. If possible, secure written confirmation affirming that the city will indeed honor and inspect your work under the stipulations of the original permit. Consider seeking counsel from a qualified attorney to safeguard your legal rights and interests in this complex scenario. It is important to remember that performing electrical work without the necessary permits or in direct violation of code requirements is both unethical and illegal. Your paramount responsibility is to uphold the safety of the electrical system and safeguard the homeowner from potential electrical hazards. By adhering to this comprehensive strategy, you can effectively mitigate potential liabilities while ensuring that all electrical work is executed to the highest standards of safety and code compliance. The National Electrical Code, or NEC, provides specific guidelines for electrical installations. These guidelines cover everything from wiring methods to overcurrent protection. For example, NEC Section 310.15 addresses ampacity, which is the current carrying capacity of conductors. This section provides tables that list the allowable ampacities for different types of conductors based on their size, insulation type, and ambient temperature. When determining the appropriate size of conductors for a circuit, it's crucial to consider the load that the circuit will be carrying. The NEC requires that conductors be sized to carry at least 125% of the continuous load. A continuous load is defined as a load that operates for 3 hours or more at a time. For example, if a circuit will be carrying a continuous load of 20 amps, the conductors must be sized to carry at least 25 amps. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. The NEC requires that overcurrent protection devices be sized to protect the conductors they are serving. The size of the overcurrent protection device should not exceed the ampacity of the conductors. For example, if a circuit is wired with 12-gauge copper conductors, which have an ampacity of 20 amps, the overcurrent protection device should not exceed 20 amps. Grounding is another important aspect of electrical safety. Grounding provides a low-resistance path for fault current to flow back to the source, which helps to trap the overcurrent protection device and clear the fault. The NEC requires that all metal enclosures and equipment be grounded. This includes metal boxes, conduit, and appliances. Grounding is typically accomplished by connecting the metal enclosure or equipment to a grounding electrode, such as a ground rod or a metal water pipe. Bonding is the process of connecting all metal parts of an electrical system together to create a common ground. Bonding helps to reduce the risk of electric shock by ensuring that all metal parts are at the same potential. The NEC requires that all metal parts of an electrical system be bonded together. This includes metal boxes, conduit, and equipment. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against arc faults. Arc faults are dangerous electrical conditions that can cause fires. SIs work by detecting the unique characteristics of arc faults and tripping the circuit breaker to interrupt the flow of current. The NEC requires SIs in many areas of the home, including bedrooms, living rooms, and dining rooms. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect against ground faults. Ground faults occur when current leaks from a circuit to ground. GFCIs work by detecting the imbalance in current between the hot and neutral conductors and tripping the circuit breaker to interrupt the flow of current. The NEC requires GFCIs in many areas of the home, including bathrooms, kitchens, and outdoor locations. Wiring methods refer to the way that electrical conductors are installed. The NEC specifies different wiring methods for different applications. Some common wiring methods include non-metallic sheathed cable, or Romex, metal conduit, and cable trays. Non-metallic sheathed cable is the most common wiring method used in residential construction. It consists of two or more insulated conductors enclosed in a non-metallic sheath. Metal conduit is a rigid metal tubing that is used to protect electrical conductors. Metal conduit is often used in commercial and industrial applications. Cable trays are open support systems that are used to support electrical cables. Cable trays are often used in commercial and industrial applications where there are a large number of cables. Electrical boxes are used to enclose electrical connections. The NEC specifies different types of electrical boxes for different applications. Some common types of electrical boxes include metal boxes, non-metallic boxes, and weatherproof boxes. Metal boxes are typically used in commercial and industrial applications. Non-metallic boxes are typically used in residential construction. Weatherproof boxes are used in outdoor locations where they will be exposed to the elements. Electrical panels are used to distribute electrical power to different circuits. The NEC specifies different types of electrical panels for different applications. Some common types of electrical panels include main panels, subpanels, and load centers. Main panels are the main point of distribution for electrical power in a building. Subpanels are used to distribute electrical power to a specific area of a building. Load centers are smaller electrical panels that are typically used to supply power to individual appliances or equipment. When working with electrical systems, it's essential to follow all safety precautions. Always turn off the power to the circuit before working on it. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electrical systems, hire a qualified electrician. Proper grounding is critical for electrical safety. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent protection device and clear the fault. This prevents dangerous voltage from appearing on metal parts of equipment, which could cause electric shock. Grounding also helps to reduce electrical noise and interference, which can improve the performance of electronic equipment. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode is connected to the grounding busbar in the electrical panel. The grounding busbar is then connected to the metal enclosures of equipment and appliances. Bonding is the process of connecting all metal parts of an electrical system together to create a common ground. Bonding helps to reduce the risk of electric shock by ensuring that all metal parts are at the same potential. This prevents dangerous voltage differences from occurring between metal parts, which could cause electric shock. Bonding is typically accomplished by using bonding jumpers to connect metal boxes, conduit, and equipment together. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, which prevents it from damaging sensitive electrical equipment. The NEC requires SPD in many areas of the home, including the service entrance and sensitive electronic equipment. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are typically performed by qualified electrical inspectors who are trained to identify electrical hazards. Electrical inspections can help to identify potential problems before they cause fires or electric shocks. The NEC is updated every 3 years to reflect changes in technology and safety standards. It is important to stay up to date on the latest NEC requirements to ensure that electrical installations are safe and compliant. The NEC is a complex document, but it is essential for anyone who works with electrical systems to understand its requirements. The NEC provides detailed guidelines for electrical installations, which helps to ensure electrical safety. Firstly, understand and adhere to the National Electrical Code, or NEC, which is a comprehensive set of standards for safe electrical installations. Secondly, properly size conductors based on ampacity and load requirements as specified in NEC section 310.15. Thirdly, utilize appropriate overcurrent protection devices such as circuit breakers and fuses, ensuring they align with conductor ampacity. Fourthly, ensure effective grounding and bonding of all metal enclosures and equipment, creating a low resistance path for fault current. Fifthly, install arc fault circuit interrupters, or size, and ground fault circuit interrupters, or GFCIs, in designated areas to prevent arc faults and ground faults respectively. Sixthly, employ appropriate wiring methods such as non-metallic sheath cable or metal conduit based on application requirements. Seventhly, utilize suitable electrical boxes for enclosing connections, considering factors like material and environmental exposure. Eighthly, implement surge protection devices, or SPDs, to safeguard equipment from voltage surges caused by lightning or other disturbances. Ninthly, ensure regular electrical inspections by qualified professionals to identify and rectify potential hazards. Tenthly, stay informed about updates to the NEC, which are published every 3 years to maintain compliance with the latest safety standards. The NEC provides comprehensive tables for various electrical calculations. For example, Table 310.16 provides ampacity values for insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth, based on ambient temperature and conductor temperature rating. These tables are crucial for determining the correct wire size for a given load. For example, if you need to run a 20 amp circuit using type THHN copper wire in a raceway where the ambient temperature is 30 degrees Celsius, Table 310.16 indicates that a 12 American wire gauge (AUG) wire is sufficient, as it has an ampacity of 30 amps at 75 degrees Celsius. However, it is important to note that other factors can affect the ampacity of a conductor, such as the number of conductors in a raceway or the presence of thermal insulation. NEC section 310.15b3 provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. For example, if you have 7 to 9 current-carrying conductors in a raceway, you must apply an adjustment factor of 0.70 to the ampacity of the conductors. This means that the 12 AWG wire that had an ampacity of 30 amps would now only have an ampacity of 21 amps, which is not sufficient for a 20 amp circuit. In this case, you would need to use a larger wire size, such as 10 AWG, which has an ampacity of 30 amps after applying the adjustment factor. Voltage drop is another important consideration when sizing conductors. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or not operate at all. The NEC recommends that the voltage drop on branch circuits should not exceed 3% and the voltage drop on feeders should not exceed 5%. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular mils, where K is the direct current constant, which is 12.9 ohms circular mils per foot for copper. I is the current in amps. D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor in circular mils. For example, if you are running a 20 amp circuit with 12 AWG copper wire at a distance of 100 feet, the voltage drop would be approximately 6.5 volts, which is more than 5% of a 120 volt circuit. In this case, you would need to use a larger wire size to reduce the voltage drop. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electric shock. GFCIs work by monitoring the current flowing through a circuit. If the current flowing through the hot conductor is not equal to the current flowing through the neutral conductor, it means that some of the current is leaking to ground. This is known as a ground fault. A ground fault can occur if someone touches a live wire or if there is a short circuit to ground. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of current and preventing electric shock. The NEC requires GFCIs in many locations, including bathrooms, kitchens, outdoor receptacles, and unfinished basements. Arc fault circuit interrupters, or RFCIs, are devices that protect against fires caused by arc faults. Arc faults are dangerous electrical conditions that can occur when insulation on wires becomes damaged or when there are loose connections. Arc faults can generate a lot of heat, which can ignite nearby combustible materials and cause a fire. RFCIs work by monitoring the current flowing through a circuit. If the current flow is erratic, which may mean there is an arc, the RFCI will trip the circuit. The NEC requires RFCIs in many locations, including bedrooms, living rooms, and dining rooms. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. Voltage surges are sudden increases in voltage that can damage sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, protecting the equipment from damage. The NEC recommends that SPD be installed at the service entrance to protect the entire electrical system. SPD can also be installed at individual pieces of equipment to provide additional protection. Electrical panels are used to distribute electrical power throughout a building. Electrical panels contain circuit breakers or fuses that protect individual circuits from overloads and short circuits. Electrical panels must be properly sized to handle the electrical load of the building. The NEC provides guidelines for sizing electrical panels. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are typically performed by qualified electrical inspectors who are trained to identify electrical hazards. Electrical inspections can help to identify potential problems before they cause fires or electric shocks. The NEC requires electrical inspections for new construction, renovations, and repairs.